This podcast is about general statistical testing exemplified with a typical t-test. When we are doing a statistical test, we have at first some kind of data, and we are asking ourselves, what kind of test do we want to do with this data? You can also start differently. You can say, well, what kind of thing am I interested in? What would I like to test for? And then I decide how I arrange my data or how I do my experiments. With a test, there always comes a null hypothesis that we want to reject or disprove. A successful experiment enables us to reject a null hypothesis. Each test has some assumptions. In the case of the t-test, the assumption is that the data is normally distributed. Some tests have variance. The t-test can be one- or two-sided, and a test needs some kind of significance level. The significance level is the level of security we want to have to say that now we have proven something. If I say I have a significance level of, for example, 5%, that means that I can live with 5% unsecurity. If we have decided about the type of test we want to use, we build the test statistics for this test. This test statistics is influenced by the data, but it applies to general random variables. So the test statistic is not something that just refers to the data. The data influences test statistics, but test statistics is meant for general random variables following some distributions similar to those of the observed data. After that, we look at the distribution of these test statistics under the typically null hypothesis. Depending on what this picture looks like, we then either reject the null hypothesis or we say we cannot reject it. And if we have been testing with a statistical program, we typically also obtain a p-value for the test. The p-value tells us how sure we can be that the null hypothesis is rejected correctly. So the p-value is the probability that the observation we have made in the data is from the null hypothesis. Or in other words, the p-value is the probability that the observed data is produced by H0, by the null hypothesis. The p-value should be lower than the significance level, then we would reject the null hypothesis. If the p-value is higher, we do not reject. Now let's exemplify this. Let's assume the following. Let us assume that we have two sellers. And seller, let's not call it 1 and 2, but X and Y. And in these sellers we have mice. These mice, they have a certain tail length. The claim is that the mice in seller X have maybe a longer tail than those in seller Y. Just generally the length differs or the length of the tails in cellar Y is longer than the one in cellar X. So what we observe is some tail length in cellar X. What we observe is the data, let's call that X bar for observation 1, X bar 2, X bar 3, and so on, let's say till X bar n. In cellar 2 or in cellar Y we also observe, let's make that maybe green. In cellar Y we observe tail lengths Y1, Y2, Y3 and so on till Y bar M. So that's our data. Now the null hypothesis says in general we don't need to specify the test yet. The null hypothesis says no difference between X and Y, between those two cellars. Now what kind of test would we like to do? Well, we are interested in the average tail length here, so a t-test is something reasonable if we test for mean values. We could also do a u-test or Wilcoxon test to test for the median of the tail lengths. That's also a reasonable question. If we would ask in which cellar the variances of tail length is higher, then this would be some kind of f-test or variance test. Let's say we decided we do a t-test. So we compare the mean. Well, the means can be computed. M bar x equals 1 over n, the sum of the x bar I, whereas I goes from 1 to n, and a mean of the cellar Y can also be computed 1 over m sum y I bar, and the I goes from 1 to capital or to small m. So this can be computed. Now the question about one-sided or two-sided, well, we leave that open for the moment. The significance level, let's call significance level alpha. Let's take 5%, this is rather standard. So, now we can build the test statistics. Now that's the first thing, right? So, now we come for test statistics. This is now something test specific. Oh, wait a second, one thing we have forgotten, something important, the test assumptions. We have to test whether the data here is both normally distributed. And let's assume we have done that test. We will talk about such tests again in the next lecture. There is Kolmogorov-Smirnov. We can make a QQ plot. There are several ways of testing normality of such data. Let's assume that this is fine. So then the next question is, what does the test statistics look like? And for the t-test, this is test statistics. Well, this is mx minus my divided by some mathematics. I don't want to give the full formula. It can be read up. And we call this thing t. Now observe something. I have not made the bars on the variables because now we talk about general random variables. Now we say, well, this is a mean value of some observation in cellar X and the mean value of some observation in cellar Y. We have general random variables, so assume that in cellar X you have 1 million mice. You take a sample of 10, right? So this is just a sample. But now this random variable here, this mx, that's the value I get when I take any kind of sample from this 1 million mice, right? So I take just some arbitrary mice and I take the mean value of their tail length, and that's what flows in here. So this is now not a number anymore. This is a concept. The concept of random variable. So, of course, I can also compute this test statistic t bar, and then I insert the m bar x minus m bar y. And this is then a number. This is a number. Okay. And this is a concept here. Let's say it like this, concept. So, in the next step now, I look at the distribution of test statistics under the null hypothesis. What does that look like? Well, let's make this down here. So what I have now is I have values of t, and on the y-axis, typically picture densities, I have the probability of observing such a t in my sample. So this is the null hypothesis, and it's the density of it, the probability density. Now let us assume that I observe my t bar that I measured in the data. This is here. So the probability that my null hypothesis produces a value that is more extreme than t bar is on the right side here. So this is if mx is bigger than my. This is the p-value. Now I can also ask myself about the p-value if my is larger than mx, and that's then just the other side. Let's mark this one in pink. So that would be this thing here. So this would be the p-value for my larger than mx. Right, so you see this in the form of the test statistics. Now if I just want to know is my unequal to mx, then I have a two-sided test. Let's make that blue. And then the p-value, then I could also have a minus t bar observed, and then the p-value is here, mx not just generally not equal my. The minus t bar is just saying that it doesn't really matter in this case here whether mx minus my is positive or my minus mx is positive. It just needs to be a certain discrepancy between the two values. So this is why we have a two-sided test. It can be either larger than we are on the right side or lower than we are on the left side. Okay, so now we have p-values Now let's just assume that we stay with the one-sided case where mx should be larger than my. Mx larger than my. And now note something. I don't make bars, right? Because the values I can measure mx bar and my bar, and then the question whether one is bigger than the other is trivial, just compare two numbers. So here it's really again a question about the concept, right? Is the general mean value of all my mice in my cellar x larger than the ones in cellar y? So let's assume that this value is, I don't know, what shall we take? 5%, 4%, let's take 4%. So that means the chance that my null hypothesis produces the observed data is 4%. If my significance level alpha is 5%, that means it's fine. I only need to have 5% security, and that's fine with me. So 4% p-value means I reject the null hypothesis and I call my experiment a success. Indeed, cellar X has larger, longer mouse tails than cellar Y. If I would have a significance level of 1%, let's say, then this would not be enough. Then I would need a p-value that is lower than 1%. in order to reject the null hypothesis and say, for my personal definition now, there is a significant increase of mouse tail length from cellar X towards cellar Y. Now, of course, such a t-test doesn't give you everything. It's a test for mean values. That's important to note here again. It could be interesting to look at the test of medians. It could be very interesting to look at the variances in both samples, and there are many other things you could think about. And for basically everything you can think about, there is an appropriate test.